Hello guys, so welcome back to our VHDL lessons. So in this recording, we're gonna do or code the JK design or JK flip flop, positive edge also. Okay, and we're gonna use our new feature that will make our life very easy, in with synchronous circuits, which is basically the process statement. So let's go into it. So basically, if we look at the design of the JK, let's open it together here. So here is the JK flip flop. It has as a circuit, it has three inputs: the JK and the clock, and two outputs Q and the Q bar. And as usual, and we're gonna see this a lot, we're gonna put the reset. The reset is really useful. It will make your life, much easy when you use it because you avoid the undefined, starting for Q and Q bar, the outputs. And remember here for these circuits, the output is a function of the inputs and its current value. So you have a feedback, and this feedback makes problems in simulation. If at the beginning, of course, because of this undefined states. So the reset will make this problem to go away because when you reset, the output will be 0 or 1, whatever you choose. Okay, so we know that here is the characteristic table for, call it truth table, whatever you like to call it. When you have 0 0, you have same no change memory state in the output. When you have J0 and K1, this is like a reset state, so Q will be 0. When you have J is 1 and K is 0, this is a set state. So Q will be 1. And finally, when you have 1, 1, you will have Q complement, which means Qt plus 1 will be complement of its current value. Okay? If it was 1, it will be 0. If it was 0, it will be 1. Okay, so let's check here, the code. So let's bring it up here. So we're gonna start first by the entity. We define here the inputs and the outputs. We have JK, clock, and reset, 4 inputs, and 2 outputs, Q and Q bar. Because of the feedback and the output is actually a function of its current value. So we're gonna define 2 signals, QQ bar, QQ and QQ bar. QQ representing Q and QQ bar representing Q bar. And then the design itself, it is a design itself. So let's bring here, the characteristic table just to compare. So in the beginning here, I'm defining the process, and as I said, the process should have a label. You can choose any label you like, call it your name, whatever you like. So I call it JK process or JK proc. So here is a sensitivity list. This process will be executed when the clock changes, because this is a synchronous circuit, or when the reset, changes. When you have a reset, whatever the clock, whatever the inputs, make our output 0. Then we're gonna use the if statement as usual to define here this truth table. If statement really, defines the truth table, it's really a truth table like programming, like just like the select with statement that we discussed in the before. Very similar to it, although there is this concept of ordering. So if reset is 1, then QQ is 0, QQ bar will be 1. Else if the reset is not 1, if the user didn't reset the circuit, then the circuit will do its job. What is the job of the JK flip-flop positive edge? When the positive edge comes, one of those 4 states in the truth table will happen. Okay, so let's check. If J is 0 and the K is 1, then I'm gonna assign, this is basically the second state here. Let's change the color to make it clear for you. This is basically the second state. which is a reset. So I put here QQ0 and QQ bar 1. And one note here is that when you assign something to the output or a signal, when you assign something, the assignment statement, we use this notation, which is, less than equal. But if you are checking on a value of a signal or an input, use just equal sign. That's really important. Here we are not assigning. Here we are not assigning. Here we are checking the value of some input or some signal. So when you check a value, not assignment, you use just the equal sign. When you assign something, assign some value to some output or a signal, you use this greater than or equal. It's not, of course, it's not that meaning, but this is how you do it. That means this less than means it's like the head arrow. It's not like less than. It's like an arrowhead. So that's basically, you have an arrow like this, and here is the head of this arrow. Okay, so that's the direction of the assignment. This 0 will be assigned to QQ. Okay, and of course the QQ bar will be 1. That's basically this, this state. Then, else if J equal to 1 and K equal to 0, which is basically the set state, then QQ will be 1, QQ bar will be 0. Then, when J is equal to 1 and K is equal to 1, the third state, or the fourth one here, okay, we're gonna complement the new value of the QQ or QQ bar will be the complement of its previous value, or its current value, basically. So that's why I'm saying here, QQ is equal to not QQ, and QQ bar is equal to not or assigned to Q bar, the complement of its current value. That's basically what I'm saying in here. That's it. Okay. One may say, where is 0, 0? You can add it, but what is the meaning of saying QQ, assign QQ to QQ? It doesn't have them, so it's not relevant. So by default, this what will happen. I mean, if J is equal to 0 and K is equal to 0, since you didn't add this state here, you will find it to occur without your intervention, without coding it. I mean, whenever we see 0 and 0, Kj is equal to 0 and K is equal to 0, and the negative edge comes, the positive edge comes, you're going to see no change at the output. Because you didn't state this, so, it will just, the system will not respond to that state. Okay? That no change in J and K. Okay? Then, we didn't finish yet, because remember QQ and QQ bar are just internal signals. So here, after the process, I make, this assignment now to assign QQ to Q and QQ bar to Q bar. Okay, and one note here that you must, know, although it's not that important here, but you must know this. I said that whenever you use a process statement between the beginning of the process and the end of the process, this is sequential, execution. I mean, the order does matter here. Okay. But if with no process, the order doesn't matter, right? So in here, we should know that the execution of that program the order of that program as a whole doesn't matter. How is this? I mean by here that this is the process statement is one statement, is counted as one statement, just like this one, and just like this one. So overall here you have 3 statements. Of course, one of them has many statements inside, but the process itself is one statement. Okay, so the order of these three statements doesn't matter. I mean, I'm sorry. This process statement can be written after Q, assign QQ to Q, or after assign QQ bar to Q bar, or in between, or this before that, whatever you like. The order between these three statements, the process statement, the process itself is a statement, and these two statements doesn't matter. Okay, but the order here does matter. That's why we check on the reset first. Okay, so that's basically the design. Let's now check the output. Okay, I have here this bench just like that. I will just put many values for J and K to check, all possible combinations like 0, 0, 0, 1, 1, 0, and 1, 1. Okay, and remember here you have many variables. It's not just the JK and the reset and the clock that determines the output. The current value of the output itself determine, the new value. So the conventional way of having loops, is not that comprehensive, we can say. That's why I tried here to, just dump some random numbers for J and K in a very long series, very long. Okay. So let's check. So in the beginning, here's the cyan or the blue signal is the reset signal. So whenever it's 1, Q will be 0, Q bar will be 1. That's basically the case. And of course, no response to the. So here there is a positive edge at 1 nanosecond, but this will not affect the output. The output will stay 0. Although, if there is no reset, or if the reset has no value, or 0, I'm sorry, then the output should be 1 because J here is 1 and K is 0. So it's a set state. Okay, now at that particular moment, reset becomes 0. Then here, when the first positive edge comes, we're gonna go back to normal operation. I mean, the circuit will do its main job, which is JK flip-flop. So we're gonna check J and K at each positive edge. So J here is 1 and K is 0, just 1 and 0. So basically it's a set. That's why Q become 1 and the Q bar becomes 0. Then Q will not change because this is just a negative edge here. Until now, the next positive edge. J is 1, K is 1. This state is the toggle state. We call it toggle. So toggle means whatever you have complemented. That's what we basically have. So we had 1 in the beginning for Q. It was 1, now it will become 0, and the Q bar was 0 become 1. Then here, positive edge again, K is 0, J is 1, so it will become 1 again. Here is a positive edge, and we have still J1 and the K 0, so it's still set state. So Q will continue just 1 and Q bar will continue just 0. Then here we have a positive edge, but J and K are 1s. So this is a toggle complement. So Q will be 0, Q bar will be 1. Again, 1, 1 again with another positive edge. So toggle again. That's fine. From 0 to 1, from 1 to 0. Then here we have a positive edge with 0, 0. 0, 0 means keep your current value. It's a memory state. So Q will remain 1, Q bar will remain 0. Here we come at another positive edge, but J is 1, K is 0, so Q will be 1. Of course, it's 1, it's already, so no change. It's not a memory, though. There's no change here because we're gonna set Q to 1, but it's already 1, so that's why it's not change, not because it's a memory. And the K is 0. Then here, for example, it's the first time to see K is 1 and J is 0. So it's a reset state. So Q becomes 0 and the Q bar become 1. And so on, guys. Okay, if you continue, you're gonna find same behavior, which reflects the JK flip-flop. Okay, guys, that was basically the JK flip-flop. Just before we go, you're gonna find here some commented lines. Okay, it's no ignore those. We can. I'm not talking about those in particular. I'm talking about those lines in here. And those basically another way to code the JK flip-flop. It's for you to practice if you like, but in a structural way, just like what we studied in the lecture. So look, this is basically the structural way to make the JK flip-flop. You need a DK flip a D flip-flop. This one is a positive edge. Okay, and you need an OR gate, you need two AND gates and an inverter. That's basically what you're gonna find here, and it's also working and working, good. You can just comment, I'm sorry. You can just comment all of that. You can just comment these three statements again. Process as a whole is a statement, okay? And uncomment those, but change Q bar internal to Q bar and Q internal to QQ, okay? Then it will be basically another way to implement the JK flip-flop, okay? With a reset also. Okay, guys, that was basically the JK flip-flop. Thank you very much for watching this video and see you in the next video. Bye-bye.